Hello and welcome to another video of Grokking the Cody interview series. In this series, we are going through the sliding window pattern. And in this video, we'll have a look at the longest subarray with ones after replacement, which is classified as a hard problem. But because we have been going through this pattern, we'll realize that once again we can go ahead and break this problem into the approach we have been taking for other problems as well. So let's get started without any further ado. So given an array containing zeros and ones, if you're allowed to replace no more than k zeros with ones, find the length of the longest contiguous subarray having all ones. So essentially here we have an additional condition. So instead of having an array which can contain any character, we have a limit that it can only have first zeros and ones. And in addition, we also have a limit that we can only replace zeros with ones. It cannot be the other way around. So let's try to brainstorm a solution in the context of sliding window pattern, which we have been going through. So here I have an array. Let's assume that we start with our sliding window. So our window length will start increasing from here until we have the number of zeros which we can replace. Everything is great and happy. As soon as we encounter a situation where the number of zeros is more than one, we will keep sliding the window forward until we encounter a situation where number of zeros in that window is less than or equal to k. So as soon as we are in this situation and we slide the window forward, we again end up having more than two zeros. So we'll keep on continue sliding the window forward until we reach a situation where we only have like two zeros within the window, which will happen here. And once we are here, we'll keep expanding the window end as well. And hence we'll encounter a scenario where we have um, the maximum or the longest contiguous subarrays with having all ones. And similarly, we'll have like exactly the same approach here as well. Instead of k equals to 2, in this case it'll be 3. So essentially the same thing. As soon as we encounter four zeros, we'll keep moving the window forward and we will continue to do. So our condition in this case is based on the frequency of zeros. So we need to ensure that in any valid sliding window, the number of zeros will be k or less than k, but it cannot be more than k. So once we encounter a situation where the number of zeros is more than k, we'll go ahead and slide the window forward until the number of zeros is again less than or equals to k. So let's try to go ahead and see what an implementation would look like. Again, I have to emphasize it will be very similar to how we have been approaching other problems as well. So we go with the max length. We'll have a window start, which will be initialized to 0. We'll have a digit frequency hash map. I will go ahead and initialize with 1 and 0, where 1 will be initialized to 0, and 0 will also be initialized to 0. So again, the same standard exercise for window end in range, length of array, and at this point we want to get the digit index with window end. If digit is it isn't, because we have initialized it either way, so we can simply go ahead and increase the frequency. Digit is equals to okay. Awesome. So what is our condition which we need to satisfy? Our condition simply is while uh, digit frequency, we want to check the frequency of 0 in the hash map if it's more than k. So this is our way of ensuring that the current window is a valid window. And while the frequency of 0 is more than k, what we'll do is we'll keep reducing the frequency of the window start element as we are moving the window forward. So this will be this. We'll keep increasing window start. And so at this stage, we have an assurance that we have gone ahead to remove any excess zeros we had above k. And this will be the point where I'll go ahead and extract the maximum length which I can have in my window, because I'm simply considering all the valid windows as I'm moving forward. Plus one, and I can simply go ahead and return the max line here. So again, let's just quickly go through the implementation and see if everything is in line with what we are expecting. So we have a max length, we have a window start, we have a digit frequency hash map where we have already gone ahead to initialize the hash map for 1 and 0. We start iterating over the array. We see we extract whichever the digit it corresponds to the window end, and we keep updating uh, the hash map which we have here. So what we want to make sure for uh, a valid window is that the frequency of zeros should never be above k, and as soon as it is above k, I start uh, shrinking the window until the frequency of 0 is less than or equal to k. Once that condition is satisfied, I'll just go ahead and extract the max len, and I can return this as an answer to my question. So let's try to run this and see if it leads to the correct answers. Okay, it seems like it leads to the correct answer. So our implementation is indeed sound. Let's quickly speak about the space and runtime complexity of the implementation. So we see the space complexity. We have a hash map. It can only contain two the digits. So effectively, it will be a constant space operation, and we are iterating through all the elements of the array once, and we also have a while loop inside. So the worst case scenario, it can be that we simply have have yeah, we effectively just yeah, potentially have zeros in the strings, and in that case we have to iterate to the whole array once. So it can be at the worst case O of n plus n. So effectively, I would assume it's O of n. So the runtime of the implementation is O of n, and the space complexity is constant space. Let's quickly go ahead and validate if it is in line with what we are expecting. Okay, indeed. So I really hope you found the explanation clear enough. Please reach out in case you should have any questions. We'll be more than happy to answer. Until the next video, have a great day.